Hello everyone, this is Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we will see Rankine's formula for column. In previous video, we had seen the different types of in condition, then what will be the equivalent length. Alright, so now we will see next as the Rankine formula for the columns. So this is the last video for this module. After that, next video we will start the third module. Okay, so in this video, we will cover Rankine's formula for column, then long column subjected to eccentric loading. So here, this derivation will be there, that is a very important derivation, and then Euler's formula. So these things we will see in this video. Okay, so first, I define the first long column and short column. So short column, so what is that? In case of short column, the value of PE will be very high. So P Eulers will be very high, therefore the value of 1 by PE will be quite negligible. If PE is very small, so definitely reciprocal of very small is very small, that is negligible as compared to 1 by PCS. It is thus obvious that the Rankine's formula will give the value of its crippling load, that is P, approximately equals to ultimate crushing load. Okay, so this value will give what? The crushing load value, that is this P will give you the crushing load value and ultimate crushing load, that PCS, right? So 1 by PCS. So that is for the short column. For long column, what happens? In case of long column, the value of P will be very small, that already we had seen. This value will be very small, so 1 by P will be what? Very large, right? Will be quite considerable as compared to 1 by PCS. So here 1 by PE value will be bigger compared to 1 by PCS. It is thus obvious that the Rankine's formula will give the value of its crippling load, that is P. So in this case, that will give the crippling load. Okay, and thus we see that the Rankine's formula give a fairly correct result for all cases of column, ranging from short to long column. So Rankine's formula we can use for both the column, either it's short or long, but Euler's formula we can apply for only long column. Hence, Rankine's formula is valid for both. So now Rankine's formula. So let's see. Professor Rankine's, after a number of experiments, give the following empirical formula for column. So what that column, either it's a short or long, right? So 1 by PR, that is PR Rankine. Okay, R is here is crippling load given by Rankine formula. So that's why 1 by PCS plus 1 by P, where P is Euler force and that Euler load, or PCS is crushing load, where PR is what? Crippling load by Rankine formula. PCS is what? Crushing load. So load is what? Sigma CS into A, that is ultimate crushing load for the column, and P is already we had seen from the Euler's formula. So that is the crippling load obtained by Euler's formula. So PR is crippling load by Rankine formula, P is crippling load by Euler's formula, and PCS is ultimate crushing load. So in these, this one is the relation. This relation between, you can say, Rankine and Euler. Then this will be the relation. Okay. So now a little consideration will show that the value of PCS, this CS is here. Okay, that P crushing or crippling load by what? Rankine's, that PCS crushing load or ultimate crushing load will remains constant irrespective of the fact whether the column is a long one or short one. So this value will not change, already we had seen in the previous slide also. Either it's a long column or short column, PCS value will remain same. Now we shall study the effect of PE, that is subscript E, P in the short as well as long column 1 by 1. So now, because Rankine's formula is valid for both, so PE for long and column according to Rankine's, what happened, that we will see. Okay, so now from the equation first, already we had seen this equation, 1 by PR equals to 1 by PCS plus 1 by P. So take LCM. After LCM, what happened? PCS plus PE will be what? PCS into PE, and that just take the LCM of this one. So P plus PCS by PCS into P. Okay. Now just take the reciprocal. So now this will get numerator and this becomes to denominator. So PCS plus P by PCS plus P. Now divide by PE. In terms of P we have to find. So divide by P. So this P will get cancelled. This becomes what? PCS by PE plus P by P means 1. So finally after dividing by P you will get this term. Right. So what we have now, or just see here. So 1 by PR equals to what? PE plus PCS by PCS into P. Once you will take the reciprocal, this will come to numerator, this will be denominator. So PR equals to PCS into PE by PCS, okay, plus PE. Okay. Now from here either take PE common or divide by PCS. So after dividing, what happened? PCS into PE divided by PE for this part, right? All divided by what? PCS by PE plus PE by PE. This will get cancelled. That becomes 1. So what we will get? PCS, this PE cancel. So PCS by 1 plus PCE divided by PE. So we'll get this value. Now substitute the above value in that equation, that PR value. So now what we will get? Now substituting the value of PCS and PE in the above equation. So in this equation, substitute the PCS value and PE value. So let's see after substituting what we will get. Okay, so now PR is this one. What is PCS? Just now we had seen in previous slide also, sigma CS into A divided by 1 plus, again PCS is what? Sigma CS into A divided by PE. So P also we are seeing here is the PE, right? Pi square EI by this one, right? So now, so just see here. So PR is equals to what? Sigma for this one. PCS is sigma CS into A divided by 1 plus PCS is again sigma CS into A divided by now PE form. So PE is pi square EI by LE square. So pi square EI by what? LE square. So this will come to numerator. So this we can write as sigma CS into A by 1 plus what? This one. Sigma CS into A into LE square by pi square E. Pi square EI. Okay. So this will be this one. So after this what we will get? Just see here. LE square by EI. EI. Yeah, I will be there. Okay. So now EI. Now for that I again we can substitute value what? AK square. So I equals to AK square. Just substitute here. So now after this what we will get? After substituting here, sigma CS into A divided by 1 plus, let's see here, this one. So this will give what? Sigma CS. Okay, I'm just separating this one. So by pi square E into what value? A LE square. A LE square by, now I is what? AK square. AK square. So A cancel, right? So now what we will have after this? So this will be sigma CS into A divided by 1 plus sigma CS into LE square by pi square E and K square, right? So now this I am just separating. So sigma CS into A divided by 1 plus sigma Cs by pi square E into Le square by k square. So can you write Le by k whole square? Right. So just instead of this, why? Because this we know this is the slenderness ratio. That Le by k is what? Slenderness ratio. Okay. Now for this one. So this constant, this sigma Cs will be constant. Already we had seen that PS Cs is not changing. So PCS is not changing. This sigma Cs also will not change. So this is constant. Pi square is constant. E is constant. So for this, Rankine given another name that as constant, that is A. So after this we can write this as, that is PR equals to sigma Cs into A by 1 plus for this constant, that is given by name, that name given by the Rankine is A, that is Rankine constant, and Le by k whole square, where A is what? Where A is, where here this A is sigma Cs by pi square E, which is called as the Rankine constant. Okay, so this will be the final PR formula in terms of slenderness ratio. Okay, so the PR is sigma Cs by into A, or this we can write in terms of that PA also, so PCS. So or like PR will be equals, this is in terms of sigma, and now in terms of P, so this will be PCS by 1 plus A Le by k whole square. So this will be in terms of PCS. So sigma Cs by 1 plus A Le by k whole square, which is equals to, instead of this just replace, okay, that PCS for this one. So PCS by 1 plus A into Le by k whole square. So this will be the final PR, that Rankine load will be this one, or crippling load given by the Rankine. Right. So PCS is what? Crushing load of the column material. Sigma Cs, crushing stress of the column material. A is cross sectional area of the column. A, the C A is Rankine constant, which is equals to what? Sigma C by pi square A, this value. L is equivalent length of the column, and K is the least gyration, right? So that least gyration is given here, that moment of inertia as A K square. So this is what? The Rankine formula. Okay, so in terms of stress or load, so this is in terms of stress, and this is in terms of load. Now for the long column subjected to eccentric load. Okay, so now we will see the Rankine formula for what? Having eccentric load. So see, consider a long column subjected to an eccentric load. So having load, so just see, let P equals to, now we are assuming those conditions whatever. So let P is equals to what? Load on the column. A, area of cross section. E, eccentricity of the load. Z, modulus of section. Y, E, distance of the extreme fiber. This Y subscript E. Yeah. Distance, Y is distance, and E stands for extreme fiber on the composite side from the axis of the column. So from the axis, whatever the side will be, like from here, an axis of this is there. Right. So this will be the extreme fiber. So distance between from axis to this extreme fiber, not here. This distance one, because many fibers will be there. No, extreme fiber, or you can say the last fiber from the axis, that distance is YE. And K is the what? Least radius of gyration, that already you know. Right. So now just see, when a column is subjected to an eccentric load, the maximum intensity of compressive stress is given by the relation. So this is P by A plus M by Z, that you know. But what about that M? Moment will be P into that eccentric distance up where that load is acting. So now instead of M, we can write P into A divided by Z, where Z is the section modulus. So now the same, if eccentric loading is not there, then this formula will be there. Once that eccentric loading will be there, then moment value will change and it becomes PE. Okay. So now, so after that, next just change this value Z. Z equals to what? I by Y E. I by y. What is I? AK square. What is I extreme? That y extreme is y L at a distance L, whatever that L there. What is this one? So now we will substitute here for Z. So now just see, after substituting, what we will get? P by A plus P, right? For this one, P already is there. For Z, what? Z AK square by YL. So this will be AK square and y extreme or YL, whatever. Y extreme is just keep y extreme itself. So that y extreme will go to the denominator. So now we have what? P by A plus PE YE by AK square. Now see, in this, here P by A and here also P by A common is there. So take P by A common. So after taking P by A common, what happened? For this term 1, in this term E into YE. Don't multiply that E and YE as E square Y. This E, already I told you, this is subscript that denotes for which fiber, that extreme fiber, and this E is eccentricity. Okay, so now this will be 1 plus E YE by AK square. So this will be the sigma max. Okay. So now crushing. So sigma, if sigma C as the permissible crushing stress for the given material, then the safe crushing load for the given column is. So sigma CS is what? Crushing. And just see, we have found just now sigma max, that is the only crushing. So this will be what? P by A into 1 plus EYE by K square. Already we have seen this one, right? So now then what will be P? Just cross multiply. So after this, what happened? P will be equals to sigma CS into A, and this whole part will get what? Divided here. So divided by 1 plus EYE by K square. So this will be P. Okay. So we have already discussed that the safe load by Rankine's formula for long column and axial load is given by the relation P equals to sigma CS into A by 1 plus ALE by K whole square. Right. So this formula already we know. So now just see, compare this formula. Okay. So see, it is thus obvious that if the effect of buckling is also to be taken into account, the safe axial load with eccentricity. So now here just see the difference. This is what? Without eccentricity. Now if eccentricity will be there, then what happens? Then this term will get added. Okay. So after this, the total will be what? P equals to, in terms of eccentricity, this remains same without eccentricity, and this term will get added 1 plus E into YE by K square. So overall, with eccentricity, this will be the value of load after combining both. Okay, so this is the final formula with eccentricity, equivalent length, and radius of gyration. Now Euler's formula. So now we will derive the Euler's formula having at eccentricity. Okay, when load is acting at some point. Okay, let's see. Consider a long column AB of length L. So this is AB is initial column having length what? L is given. L is fixed at A. So now here it's given, it is fixed at A. Free at B. So this was free and carrying an eccentric load as shown in figure. So actually load should act, already we had seen load should act here at the beam. But eccentric load means at what distance the load is acting. So suppose just here something is connected. Right, some plate is there or something is there, and on that you are applying load instead of this one. Okay, so that distance is called the eccentricity after how distance that is acting. So earlier already we derived this as, we have taken this distance as A. Now from that one, no, load is not acting on this one. Load is acting somewhere else, where that at a distance E from the end B1, which is earlier B. So after deflection, this becomes B1, and load is acting at a distance E from the B1. So now total distance will be what? This total distance, because once we have to find the moment, we have to take the total distance, force into perpendicular distance. So for this P, this will be V and perpendicular distance will be A plus E, right? And here once we have taken this one, then another moment will be what? This is because outside, so it's a what? P, okay? Or just see here, if we will take this to positive, then this will be negative. So total x will be what? This total is A plus E, and this we have to remove. So from here, this distance only we have to take, right? So that will be x plus A minus E. Let's see. So as a result of loading, let the beam deflects into a curve from AX1, B1, this is subscript, such that the free end B deflects through A, that is distance, okay, and occupies a new position B1, right, as shown in figure. So now next, now consider any section x at a distance small x. So x is the section at a distance. So everything same, just this extra term you have to add from the Euler one. Okay, that already we derived. One in fixed, other free. In the same condition, just you have to add this moment term. That's all. Right. So now thus the let P equals to critical load on the column, E eccentricity of the load, Y deflection of the column at x. So at x section, what is deflection? That is small y. Thus the eccentricity of the load P at x equals to A plus E minus y. So this will be what? Total is x. So total is A plus E, and at this point x is there. So from here, this how much deflection is there? A plus E minus y. Now because of that, what will be the moment? So moment due to load will be what? M equals to plus P into the distance. So distance is A plus E minus y. So that will give you what? M equals to, just multiply with plus term. So P into A plus E minus Py. Or you can just multiply like PA plus PE minus PY. Here I did Y because this P in here we have to take this side. Once we will apply the bending moment equation, this PY should be the other side. So just take this only, and so after multiplying P into A plus E minus PY. So this will be the moment equation. Now we have the moment equation. So for all the cases, the important thing is only find the moment equation. Once you have the moment equation, substitute in the bending moment formula, and after that take Py term to the other side, that is left side, and then write their general formula and just put the boundary condition and solve it. So same here also we will do. Now we have M. Okay, so next we will apply the bending formula, right? So this is formula, right? Ei d2y by dx square equals to M. What is M here? P into A plus E minus Py. After this, what we will get? So just same again, what you have to do? Coefficient of d2y by dx square should be 1. So what we have to do? Divide Ei throughout. So after dividing Ei, this Ei will get cancelled. So here, and then P dot Ey, that is P into y by Ei equals to P plus P into A plus E by Ei. Right. Now for the general solution, you know, for this one, these two term will be same. Only the thing, whatever other than Pi will be there, that you have to add. Earlier also we had seen, right? So P by Ei in this case already is given. In one case it was not there, so what we did, we multiplied and divided by P. But here P by Ei already is given, so P by Ei no need to do. Remaining thing we have to just add. So general solution of this is what? Y equals to A cos x into root P by Ei plus B sin x into root P by Ei plus what is left here? A plus E. So just add A plus E. So this is the general solution of this differential equation, where A and B are what? Constant of integration. Now what we have to do? Apply the boundary condition. So when x equals to 0, y equals to 0. So just see here, at x equals to 0, y is what? There is no deflection. So y is also 0. So after substituting here, at x equals to 0, y equals to 0, put here. So what we have? Y equals to 0. So 0 equals to A cos x 0. So 0 root P by Ei, okay, plus B sine 0 root P by EI, okay, plus A plus E. Okay, now after putting 0 into this is 0, sine 0 is what? 0, so this term will be 0. So here 0 into this is 0, sine cos 0 is 1. So 0 equals to A into 1, A plus E. What we have to find from here? A. So A will be equals to what? Minus of A plus E. Now we have A. Next is what? We have to find B. For that what we did? Differentiate. Right. So then let's differentiate and then put the boundary condition. So after differentiating, right, this will be same for all. Once you will differentiate that one, that will be same. Why? Because this is the constant term. That will get 0. Differentiation of constant term is 0. So already we had seen many times differentiation of this is what? Dy by dx equals to minus A root P by EI sine of x into root P by EI plus B root P by EI cos of x root P by EI. So this is the general solution. Now next what we have to do? We have to apply again the boundary condition. Okay. So now just see the figure. At x equals to 0. So at x equals to 0, what will be the slope? That also will be 0. So at x equals to 0, we can say dy by dx also will be equals to 0. So put here now x 0 and dy by dx equals to 0 in this one. So dy by dx is 0, okay, equals to minus A root P by EI, okay, sine x root P by EI, okay, this term, plus B root P by EI cos x, that is 0, so this is also 0, right, 0 root P by EI, okay. So sine 0 into P by root EI what? 0. So sine 0, 0 means this whole term will be 0. So 0 equals to 0 plus this is 0. 0 into root P by EI is 0. So cos 0 is 1. So B root P by EI into 1 is B root P by EI. So now again what? 0 equals to B root P by EI. So again here condition will be there, either B should be equals to 0 or P should be equals to 0. Right. So let's see which one will be 0. So again, because P cannot be 0 here. Okay. If P will be 0 means there is no load is acting. So we can take only B as 0. So see, a little consideration will show that either B is equal to 0 or root P by EI equals to 0. Since the load P is not equal to 0, because if P load we will apply as 0, then what happen? It won't bend. Means load you are not applying. There is no crippling in that column. It is thus obvious that B is equals to 0. Hence, B only probability is there, that is 0. Substituting the value of A and B. So A what we got? A equals to minus A plus E and B is 0. So this B term will be what? Totally 0. So Y equals to, this is for A. Right? So A is minus A plus E cos of x root P by EI plus AE equals to, okay, this one. So after this again what we can take? We can take A common. Just see similar is there. Earlier we took A common, here A plus E term we added. So A plus E term common. So after taking A plus E term common, what we will get? Here, let's see, for this term 1 and this is minus. So 1 minus cos of x root P by EI. So A plus E, or you can just write here like A plus E in bracket. So A plus E into 1 minus cos x root P by EI. Now again, so because we have to remove finally this x, substitute what? Again, third boundary condition. So at x equals to L, what will be y? Y will be the maximum deflection, that is A. So substitute here. So y equals to A, right? So here y equals to A. So now just substituting A equals to, sorry, A equals to now this one. So A plus E, right? 1 minus cos, what we have to put? X equals to L. So put here L. So L root P by EI. Okay. So this is cos of this one. Right. This A will come this side. Then what happened? It becomes 0 or sorry. Okay. So now what we have, this will be, and take this side, multiply first this one. Okay. So after multiplying, just see, we cannot directly cancel. First we have to multiply this one. So that implies A equals to A plus E into 1, that is A plus E, minus A plus E into cos L root P by EI. Okay. So now take this to this side, or take this side and this to this side, so that this becomes positive. So now I'm taking this to this side. So A plus E, that implies A plus E cos L root P by EI, which is equals to what? A plus E, already we had, minus A. Right, this A. So A cancel, means A plus E cos L root P by EI equals to what? E. Okay. A plus E cos root L root P by EI equals to E. So now from here A plus E will what? So now A plus E will be equals to what happened? We have to just divide this term. So that will be, alright, keep this one and then this will be divided here. So A plus E equals to what? E divided by cos L root P by EI. So this we can write as A plus E equals to E, 1 by cos is what? Secant. So secant L root P by EI. Okay. So this will be this one. So A plus E equals to E into secant L root P by EI. Okay. Next. What we see, that maximum bending moment occurs at B is equals to P into A plus E. At B only maximum bending moment will be there. Here maximum bending moment, M max is what? P E secant L root P by EI. Okay, so now just substitute the value whatever we will get. So maximum bending moment, we got this one, right? Maximum bending moment should be what? M max equals to P E secant root L by P into EI. That just now we derived. So from here same, sigma max will be equals to what? P by A plus M by Z. P by A, M is what? This one, moment, P E secant L root P by EI, and divided by this Z. The equation 2 and 3 are valid for the column with one in fixed and other free. So this one is valid for, and the previous what we derived, that first one, right? So second and third with one in fixed and the other free. Now what condition what? For one in fixed and free, L equals to 2L. So here L equals to LE by 2. So substitute here. This L as LE by 2, because this equivalent length we know, one in fixed and one in free, that equivalent length is equals to 2L. So that we will use here. So from this L equals to LE by 2. So substitute here. So after substituting, what we will get? Substituting L equals to LE by 2 in equation 2 and 3 we will get. So in this, if we will put, so this is what? Second equation, this is third equation. So M equals to P secant capital L by 2 root P by EI. P secant capital L E by 2 root P by EI, or equivalent length by 2 root P by EI. So this is for the maximum. And maximum compressive stress, this is what? Maximum bending moment. And this is maximum compressive stress will be what? P by A plus M by Z. After substituting, already we had seen P by A plus 1 by Z into PE secant root LE by 2 root P by EI. So this is the maximum compressive stress, and this is the maximum bending moment in case of what? Eccentricity. Now this is the last topic of your second module, that is Southwell plot. So by using this, just same thing here. Okay, just here. Southwell in 1932 method is a plotting technique which is used for estimating the critical load and the initial geometric imperfections of a column. So let's see here. Estimating the critical load and initially imperfection in geometric, right, or geometric imperfection of a column by using its experimental load and deflection data at load smaller than the buckling load. So whatever the buckling load is there, right, apply lesser load so that you can find, that means whatever the experimental data is there, with that you can find where is the geometric imperfections are there, right. So it's a given by Southwell, that's why its name is Southwell plot. So just see here, in this case it's a lateral deflection, lateral centroidal deflection versus load. So let's see here, it's the load versus deflection we have to find, that is the experimental data. So this black one is the experimental one and red one what we derived right now. So U is U naught by 1 minus P by PCR, that we crippling. So based on that, just see here, you can see experimental what is they got and theoretically what we found out, what we derived, right, very slight differences there. So instead of calculating that is by theoretical, just go with the experimental value, see whatever the experimental value you are getting and then just compare. You can see almost it will be similar to the experimental value. Experimental and theoretical are almost of the same values. Okay, so that's why we are using the Southwell plot just to determine what the initial deflection where it will be there. So plotting technique which is used to estimate the critical load and the initial geometric imperfection. So the imperfection is what? The deflection, right? So load and deflection. So for how much load? So see here, for 6K IPS, what will be the deflection? Just go to here, 6 where it comes. So experimental they got like this, around 0.772 like that. But at the same time, load what actually what they, that means by formula what they got here, right, slightly greater than that one. So it's around 0.072 was there, so 0.75 or 76 it will be there. So by plotting the curve with the experimental data, we can find, that means for that particular load, how much deflection will be there or how much imperfection will be there, that we can determine simply by putting those value in the chart. After drawing the curve with that chart or those values, then we can directly find. Or suppose someone asks for 1.5 deflection, right, that is 1.5 inch deflection, how much load should be there? So just go by 1.5. So just see here at this one, so almost around 11 point, you can say 5, 11.6 or like 11.9 up to, if you will take very near to that one, so 11.9 K IPS value will be there. So in similar way, load and deflection. So this is the case of lateral centroidal deflection. It's not necessarily only the lateral centroidal deflection, we can, any type of deflection is required. Just already it's here, that's why this word is used, initial geometric imperfection. It is not necessary only the lateral centroidal deflection will be there, longitudinal also will be there, and some sharpies also will be there, right? So depending upon that, whatever is there, that you have to take the deflection, you have to take along the x-axis and load along the y-axis. Then that will show what, and that plot is called as the Southwell plot. So see here in this case for the various one. So you can see U by P in what, inch per Ki dot load, right? And here it's new in terms of this one. Here this is phi angle, that is in terms of radius, because in terms of radian also, if angular deflection will be there, that will be in terms of angular radiation. Similarly phi, nu, phi, right? Here U by P square, U by P, U by P, phi by P, phi by P, phi by P square. So phi is what? Radian, right? Pi square is KIPS, so KIPS square. Phi is here radian and P is KIPS. So just see here one thing, whenever we are taking that symbol phi by P, here you can see it's from the this one, is starting from here, but in case of p square, it's starting very close to this one. So here also you can see, but in this case, if you are taking u, then in case of u by p square, it's starting from here, but in case of u by p, it's closer to the origin. So like whatever the different conditions of the plot is there, that means with deflection, whatever the type is there, the distance or deflection in anything by applying the load, that we can plot the curve, and according to that we can find for that particular deflection or that term what was there, this one, imperfection. So with that imperfection versus load, that is called only the south well plot. Once you know that load, you can find because of that load how much imperfection will be there, or if you know the imperfection, then how much load applied for that imperfection, that you can find. Clear? Let's see. I am recalling quickly once again this Euler formula. First this one. Okay. So now Rankine's Euler formula is required. So this already we had seen that 1 by PR equals to what? 1 by PCS plus 1 by P, where PR is crippling load by Rankine formula, PCS is ultimate crushing load, P is Euler's formula. So this already we derived, this we know, sigma CS. Just substitute here, or take first LCM this one and then substitute. Choice is yours, should not necessarily take the LCM. After putting these values, also you can take LCM and simplify. Just anyhow you have to find the value of this one, where PR you have to find in terms of PCS. PCS, for that you can replace this one, P you can replace this one. Okay, so after this, if you will take LCM and then you can substitute. So after substituting here, the next step is what? Just replace I in terms of AK square, because I is moment of inertia and K is least radius of gyration. So what happened? A will get cancelled. After that, you will get this one. Okay, now after simplifying, this will get here, where A is called the Rankine constant, which is this one, sigma CS by pi E is pi square E. Already we had seen sigma CS in case of long or short column, it remains constant. That's why all the three terms are constant here. So Rankine given name as Rankine constant, and that is denoted by small a. So for this one, after writing a small a, you will get sigma CS into A by 1 plus A into LE by K whole square. In terms of if you want to write P, then sigma CS into A is what? PCS. Okay. So these are the meaning. So A is here, sigma CS by pi E square. Next, come to the Rankine formula. So for that, sigma max is what? P by A plus M by Z. Now in terms of eccentric load will be there, then that P will be M will be P into A. So P by A will be P by A, M is P by E, and Z is this one. What is Z? Section modulus, which is I by Y. So I is what? AK square, Y is Y. So substitute here. After substituting, you will get this one. In both the term, P by A is constant. Sorry, P by A is there. So take P by A common. So after taking P by A common, 1 plus EY by K A square. That is the sigma max. Now, what happened in case of permissible crushing? Sigma max is only becomes equals to sigma CS. Sigma CS will be P by A into 1 plus EY by E. Now, from here find P. So P will be what? Sigma CS into A, and this will get divided here. So by 1 plus EY into by K square. Now, this already we know, right? From the Euler's one, P equals to sigma CS into A by 1 plus A L E K square. Just now we derived this one. So here A is what? Rankine constant. So after by combining those two, the P value will be what? Just by this term, it will get added here for this one, right? So this is the rank for the Rankine. Now the derivation, the most important derivation from this chapter. Alright, so this is one of the most important derivation. So now just see what was the condition. One end is fixed, another one is free, and load is acting at an eccentric distance E here. Right? So this total distance will be what? From here to here, A plus E, and this is given as at this point Y. So what we have to take from here to here? So this distance will be what? A plus E minus Y. Now for the moment, what will be that? A plus E minus Y into P. So here, P into A plus E minus Y. Because this side it's going, the moment will be positive. So after multiplying this to this term and then this to this term, so M equals to P into A plus E minus Py. Okay, now just write the new moment equation, that is EI d2 by dx square equals to M. Substitute the value M. Next, take this side and then divide by EI. After dividing, you will get this one. So here, the general solution of this is this one, and I already told whatever the excluding P by EI, whatever the thing is there, just add that one. So here plus A plus E. Right? Now apply the boundary conditions. So again, you have to apply 3 times boundary conditions. So first was what? At x equals to 0, y equals to 0. With this, you will get A equals to minus of A plus C. Next step is what? Differentiate. After differentiation, this will be the differentiation. Next, at x equals to 0, dy by dx equals to 0. Then after substituting the value, you will get 0 equals to b root p by EI. So here, either p will be 0, root p by EI will be 0 or b will be 0. But p will not be 0. Means here, definitely b by EI will be, b will be equals to 0. So after once b is 0 means what? Second term we can directly remove, because after putting the value of b, that term will get, that becomes 0. So substitute value of a and b. So a is this one, y equals to minus a plus e. So a cos was there, right? So minus a plus e cos this one, and sine terms totally becomes 0, and this term remains there. So now take a plus e common. After taking a plus e common, it becomes 1 minus cos root x root p by EI. Now third boundary condition, at x equals to L, y equals to A. Okay, so after substituting here, right, that y equals to A, just now first multiply this to this one and then this to this one, and take this A to the other side. So after that, what you will get? A plus E cos L root p by EI equals to E. Hence A plus B will be equals to what? Just this will get divided here. So A plus E will be equals to what? E by cos L root p by EI. So this is your A plus E cos pi. So that is M max, right? So PE secant L root p by EI. Now that is the maximum bending moment. Now maximum stress, that comparative stress will be what? Sigma max equals to P by A plus M by Z. Now what we got? M, just now we found PE secant L root p by. So substitute here, P by A, M is this one by Z. So this will be what? Sigma max. So now in second and third. So put value of what? L equals to 2L. From that table earlier, we find in case of one in fixed and other is free, that equivalent length is equals to 2L. So L will be equals to what? LE by 2, that equivalent length by 2. Substitute here and here. So after substituting, what you will get? M max will be PE secant, and here this L becomes LE by 2. And similarly here this L becomes LE by 2 for this case. So sigma max will be equals to what? P by A plus 1 by Z into PE secant LE by 2 root P by EI. So these two are the final formula by the Rankine. So M max is what? PE secant LE by 2 root P by EI, and for maximum compressive strength, sigma max equals to P by A plus M by Z. That will give you what? P by A 1 by Z into PE secant LE by 2 root PI. So let's see, when you are writing this, make sure this should be there in the bracket. Why? Because this total is the argument. Whatever the value, if you will get secant of that one, suppose you are getting this value as 30, then secant 30 value you have to write. So put proper bracket. It's not like that this will be only with the secant value and LE by 2 just get multiplied. No, LE by 2 is not getting multiplied with the whole. LE by 2 will get multiplied by what? Root P by EI only. And whatever after multiplying, you will get the value. Secant of that value you have to take. So proper bracket is very important. If you will not put the proper bracket, definitely you will get a mistake and your answer will be different. So always use proper bracket wherever you are using. If your complex or long equation type is there, make sure to use proper bracket, then it will be easier to identify or to solve the question. Next is Southwell plot. Already we had seen, that means Southwell plot by experimentally whatever the imperfections are there, that is by this Southwell plot we can find. If we know the load, then we can find the deflection. If we know the deflection, then we can find the load. That deflection may be of any type, either it's a lateral, angular, linear, or different types. So whatever that means simply load versus deflection curve is Southwell plot. With that we can find whatever is missing by the given experimental data. If experimental data is given, plot the curve, then see for what load how much deflection will be there, or if you want to find the load for that particular deflection, then that deflection, how much load is coming into the graph, that will be the load acting on that one. Okay. So these are the different type of this one. So already we discussed. Okay. So for your reference, you can refer this book, that is Strength of Material by R.S. Coney. There you can find these things. So if you have doubt, you can just comment or you can contact me, okay, regarding your doubt.
Like, share and subscribe. Hit the bell icon for more updates.